In this video, I'm going to cover the three main rules of exponents: the product rule, the quotient rule, and the power rule. And so, first the product rule. How do we handle something like this? X to the second times x to the fifth power. Alright, so here I'm multiplying two numbers. They have the same base, x. The exponents are 2 and 5, respectively. And so, you may recall that this is going to be x to the seventh. We really have two reasonable choices. Either we add the exponents or we multiply them. And how do we know what's what? Well, x squared is x times x, and x to the fifth is x times x times x times x times x. So it's a product of 2 x's and a product of 5 x's, and that makes 7 x's. So it turns out that this is why we add exponents under this situation. Get x to the seventh. So here we have the power rule, and I'm going to write it on the right side of the board here. So let's see, we'll call this this is the product rule. I meant to say product rule. And product rule in general says that x to the a times x to the b is x to the a plus b. So I think it's good to learn this in your own language. My language is this: when you multiply two numbers of the same base, you keep the base and you add the exponents. That's the product rule. Okay, that's when we add exponents. Now, I should say technically, this, for right now, we only know this holds when a and b are positive whole integers, positive whole numbers. And we haven't dealt with negatives yet. We haven't dealt with fractions or other kinds of numbers. So, but it's easy to show this mathematically if you had to prove it. It's not hard all that hard to show, provided that a and b are positive whole numbers, numbers we count with. Because literally, it's a matter of counting a product, a repeated product. All right. Well, there's another rule that goes right with this one, the quotient rule. And oops, let me fix my spelling here. Okay, is that right? Yeah, you can see that. The quotient rule says that when you divide two numbers with the same base, you keep the base and you subtract the exponents, top minus bottom. There you go. So let me give you a quick example of why that's true. So suppose and this is not a formal mathematical proof, it's just a verification of this rule. So suppose you had x to the sixth over x to the second. And it's kind of popular among students to divide exponents and get x to the third. So that would be a common error. Not that common, but when people mess up this problem, that's where they'll mess it up. They'll divide exponents rather than subtract them. But you can see that the top is a product of 6 x's. The bottom is a product of 2 x's. And 2 of these will cancel out, leaving 4 left over. So it's x to the fourth, isn't it? Now you normally would not do this. We would write x to the 6 minus 2, x to the fourth power. So the quotient rule, you subtract exponents. The product rule, you add exponents. Subtracting is top minus bottom. Okay, one more of these rules. The power rule works this way. Okay, the power rule says that if you have an exponent number in parentheses raised to another exponent, then you multiply exponents. So x to the a in parentheses raised to the b power is equal to x to the a times b. So let's see an example why that makes sense also. So kind of a similar idea here. I like for you to see why these things work, because we have really very few rules in mathematics. One rule is, how do you define exponents? Another rule is the order of operations. Most everything in math is not really a rule, it's a theorem. It's something that logically follows from something else. There's a chain of logic which justifies the statement of a theorem. And it turns out the product rule, quotient rule, and power rule are theorems. And so they're mislabeled as rules. They're not truly rules. They're truly theorems. But I want you to come away from this knowing that we just don't make up this stuff. There's not a some committee of gray-haired mathematicians that meets periodically to make up rules and torture students. These things are followed logically, in logical progression. They're sort of out of our hands. We're uncovering how the nature works in mathematics. So, anyway, suppose we had x to the fourth raised to the third power. Okay, well, the third power means I'm going to multiply 3x to the fourth together. So this number in parentheses, which is grouped inside the parentheses, is raised to the third power. It means I multiply 3 of them. And this is, well, according to the product rule, we would add these, wouldn't we? Or you could write it all out and then be 12 x's all together. So literally it's x to the 4 times 3, which is x to the 12th. So there's an illustration of the power rule. As you can see, we have added, subtracted, and multiplied exponents. And you might wonder, do we ever divide exponents? We do. We do divide exponents. But not yet. We're not ready for that one yet. So that'll come in somewhat later in the course. So I'll got to keep you hanging on that. All right, I want to show you one other problem related to all this, and it involves multiplying numbers with different bases. For example, suppose that you had 2 to the third times 3 to the second. Okay, so this, if I put this on a test, the common error would be to get 6 to the 5th power. All right, so this is wrong. I'll emphasize this. Wrong would be to multiply the bases and add the exponents. So we're not multiplying bases with these exponent rules. We're just retaining the same base when the bases are the same. We don't multiply bases together. We add, subtract, and multiply exponents. That's what we mess with the exponents. We don't mess with the bases. So this is absolutely wrong. It's really easy to see. By the way, 6 to the 5th power is 7,776. And I've known that from years of playing the dice game Yahtzee, where you roll 5 dice. The number of different dice combinations is 7,776 when you roll 5 dice. All right. What is it really? Well, this is correct. 2 to the third is 8, and 3 to the second is 9. 8 times 9 is 72. So this is much smaller than 7,776. And another way to justify this is the order of operations, say to deal with the exponents before we multiply. So the order of operations, which is how we define our operational language in algebra, and that is a rule, does say that we're supposed to interpret this as do the exponents first and then multiply. So another reason why that's only 72 instead of this monster number here. Okay, well, that's enough for now.